Our goal now is to construct the standard bivariate normal with correlation rho. Now, if we look at what our task is, we have to show that the random vector xy can be written as a linear transformation of IID standard normals. But x by itself is standard normal, and separately y by itself is standard normal. The problem is that they're not independent, they're correlated. So let us save ourselves a little trouble. Let's start with x. So x is standard normal. And by this I mean take any standard normal and call it x. And now take another standard normal z independent of x. And what we're going to do is see if we can express this. Our standard bivariate normal with correlation rho, we're going to see if that can be written as A times this independent standard normal pair plus some B. Because if it can, then xy is bivariate normal by definition of the multivariate normal. So is this possible? The first thing we notice is that if this has to be the case, B has to be 0. Because the mean vector of xy has to be 0, and the mean vector of xz is 0, and so you can't have a shift. So B is equal to 0. That's fine, that simplifies our lives. And now we have to see if we can find an A such that xy is equal to the matrix A times xz. Well, look at the first row. X has to be equal to the row AB dot product xz. And so that is telling us right away that A has to be 1 and B has to be 0. So I have 1, 0, and then CDXZ will at least give me the right first coordinate. It's going to give me X at the top. And now I need the second coordinate to be Y, so I'm going to get CX plus DZ better be Y, and we'll have to find, if I can, the right coefficients C and D. So why don't we start with the correlation? So the correlation between X and Y is actually, in this case, equal to the covariance between X and Y because the standard deviations are 0. Standard deviations are 1, excuse me. Okay. This correlation is what we're calling rho. So let's calculate the covariance between X and Y using our new expression for Y. Now, the covariance between x and x is the variance of x, which is 1. The covariance between x and z is the covariance between two independent random variables, and therefore that is 0. And so I just have this is equal to c. And so I started with the correlation rho, which was the covariance xy, and I showed that the covariance xy is c, and therefore c is rho. And so now I am building my matrix. I have my matrix A is 1, 0, rho, and now I have to figure out D. So what conditions have I used? I have used the fact that xy has to have mean 0. I have used the fact that the correlation has to be rho. The only other thing that I have to ensure is that the variance of y, remember I'm constructing y, the variance of y has to be 1. And so 1 is equal to the variance of cx plus dz, which is c squared and I can do this because I took x and z to be independent. And now the two variances are 1 because x and z are also standard normal. So 1 is equal to c squared plus d squared. And we already know that c is rho, so rho squared plus d squared. So I can take d equal the square root of 1 minus rho squared. And so if we go back up here to our expression for y, what we have said is that then y equals cx, that is rho x, plus root 1 minus rho squared z will do the job. In other words, what we have shown is that for xy to be standard bivariate normal with correlation rho, you have to have x standard normal and y must be rho x plus root 1 minus rho squared z, where z is standard normal independent of x. A couple of remarks about this calculation. First, it has been largely an algebraic calculation equating means, variances, and correlations. But there is a very clear geometric interpretation. You will be noticing there's rho and root 1 minus rho squared, so it looks like a cosine theta and a sine theta. There is a clear geometric interpretation which you will explore in your lab. From the point of view of prediction, there is something very interesting has happened here. We have said that if x and y have the standard bivariate normal distribution with correlation rho, then you can think of y as a linear function of x. For that, it's rho x plus some random noise. And that observation is going to be really important when we try to predict y based on x. Linear signal plus normal noise is the foundation of the linear regression model. And some of you may remember that in data 8 we told you that the residuals of in simple regression have a variance that involves a root 1 minus correlation squared. And there it is, you see it. So we will now use this expression for y in terms of x and independent noise to predict y based on x.